Hello everyone, and today I'm going to discuss about Dalton's atomic theory. Before going straight into the postulates of Dalton's atomic theory, I would like to explain something to get an initiative to the concept of atom. Now, if you take a piece of any material, maybe plastics, maybe wood, maybe a piece of soap, maybe a piece of paper, whatever it is, or a piece of metal. If you take any piece of material and if you divide this material into smaller and smaller pieces, say you cut it into smaller and smaller pieces, and what will you end up ultimately? Will you end up with a very fine particle which is as it is, and you can't divide it anymore? Or will you be able to divide even this particle and go on like that indefinitely? What is your answer? Now, to answer this question, in the past, some philosophers had different ideas. For an example, people like Democritus, people like Democritus explained that matter consists of tiny particles which are not further divisible, not divisible. But meanwhile, some other people like Plato, like Aristotle, the famous philosophers, now they believe that there cannot exist, there cannot exist indivisible particles, indivisible particles. Now their idea was that matter can be continuously divided, and further divided into finer and finer particles, and we can keep going indefinitely. But actually, none of these ideas had any proof. Even the particle theory of Democritus, and he named these particles as atomos, which means not further divisible. But none of these ideas were proved with any experimental data like we do in today's science. These were just ideas. That's why we call them philosophers and not scientists. They are not scientists. They are just philosophers because they don't deal in experimental. They didn't deal in experimental data. They just express their idea about something. That's what philosophers do. Now, before these ideas, of course, ancient people who were curious about their surroundings believed that their surroundings or the matter around them is made of four basic elements, four basic elements, and they were fire, water, earth, and air. But now we know that this idea is completely wrong, because even earth is made up of elements such as silicon and oxygen, and air is a mixture of nitrogen, oxygen, carbon dioxide, and such gases. And water is also made of elements like hydrogen and oxygen. And of course, fire is actually ionized gaseous atoms, which is we now call as plasma. Now, therefore, later with scientific data, people developed the idea of atom, and the foundation for the idea of atom was uh, actually put by Democritus. And later, some English scientist called John Dalton put forward a theory now we call as the atomic theory of matter. Now, Dalton's atomic theory actually is based on this particle theory of Democritus. John Dalton put forward four postulates explaining his atomic theory of matter. We will discuss one by one. So this is the first of the postulates of Dalton's atomic theory, and it says that all matter consists of very fine, indivisible, discrete particles called atoms. Now, this idea of atoms is pretty much the same as the idea of Democritus, who said matter is composed of fine particles called atomos. And actually, the term atom comes as a derivative of the word atomos. So both Dalton and Democritus had the same idea about the smallest particle of matter, that is the atom. And according to Dalton, this atom cannot be, or this finest particle cannot be further divided or subdivided. But actually, there is a problem associated with this first postulate, because with the current knowledge in chemistry, we know that even atoms are composed of subatomic particles known as electrons, protons, and neutrons. Now, there were no techniques available in the times of John Dalton to view atoms. In those times, scientists had never seen atoms, although they had the idea of atoms. Therefore, they didn't know the presence of electrons, protons, and neutrons, which are actually the components of atoms. These are called subatomic particles. Subatomic particles. Atomic. So there is this problem with the first postulate of Dalton's atomic theory. But of course, the smallest particle that is associated with chemical reactions is actually the atom. Smallest particle associated with chemical reactions is actually the atom. These guys, electrons, protons, and neutrons, they don't actually involve in chemical reactions. They are what composes these atoms, but atom is actually the smallest unit which can participate in chemical reactions. Therefore, actually, there is some truth to this postulate, but the problem is that this term indivisible, these particles, these atoms are actually divisible. The second postulate of Dalton's atomic theory explains that all atoms of an element are identical in all aspects, but those of different elements are different in all aspects. So we can actually divide this second postulate into two parts like this. One part of it explains that atoms of an element are identical in all aspects in the sense mass, volume or the size of the atom, and appearance, so and so. These are the aspects Dalton talked about. And meanwhile, those of different elements, the atoms of different elements, are different in all these aspects. For an example, if we take carbon, according to Dalton's second postulate, all the atoms of carbon should be identical. That means they should have the same mass, same volume or size, same appearance, so and so. And if we take a different element, its own atoms, say nitrogen atoms are all equal, all identical. That means they have the same mass, volume, size, appearance. But according to the second part of Dalton's second postulate, it explains that atoms of carbon and nitrogen should be different in all aspects, such that mass, volume, size, appearance, all these things, all these qualities are different in carbon atoms and nitrogen atoms. So you can't compare, you can't actually show any similarity between a carbon atom and a nitrogen atom. Now this second postulate is also having some issues. The issues are, if we consider the first part of this statement or this postulate, all atoms of an element are identical in all aspects. But with today's chemistry knowledge, we know that there is a concept called isotopes. You may have or may not have heard of this term, isotope. Now, isotopes are atoms of the same element but with different masses. These are relative atomic masses: carbon 12, carbon 13, and carbon 14. All the three are carbon atoms, but the difference among them is that they are different in masses. So this concept of isotopes, which actually I will be explaining in detail in further videos, this concept of isotopes means that the first part of Dalton's second postulate, the second postulate of the atomic theory, is actually invalid. And if you consider the second part of this statement, different elements, the atoms of different elements are different in all aspects, that also sometimes not valid. According to this statement, carbon atoms and nitrogen atoms should always be different. But if we consider the C14 carbon 14 isotope of carbon and nitrogen, which is also having a mass of 14, both these are almost equal in masses. They have different electrons, of course, but electron masses are ignored usually. We can ignore the mass of an electron. Carbon has 12 electrons while nitrogen has 14 electrons. So there's a difference of 2 electrons, but approximately it is very similar in masses, because when we compare to the mass of an atom, the mass of an electron is actually negligible. So these are called isobars. Isotopes, isobars. Isobars are atoms of different elements having the same mass number or the same mass. So the presence of isotopes and isobars means the second postulate of Dalton's atomic theory is actually not quite correct. The third postulate says atoms of an element never change into atoms of a different element, such that atoms can be neither created nor destroyed. during a chemical reaction, of course. For an example, if we have two elements reacting, say A plus B, to give some product, let's say AB. Now, according to the third postulate, atoms of element A can never be changed into a different element. Atoms of A cannot be changed into B or something else, say C, D, if these are atoms of different elements. An atom of A will never change into an atom of B. An atom of A will never change into an atom C. It will never change into an atom D. So same goes for atom B. Element B's atoms will never turn into something else. This was the idea of the third postulate. But of course, there is a problem with this postulate as well. If we consider a radioactive element such as uranium, this is radioactive. It undergoes a series of decay reactions, and finally becomes a lead atom. A uranium atom undergoes a series of decay reactions to become a lead atom, which is of course not radioactive, and this is stable. Uranium is unstable. So uranium is an element different to lead, but due to radioactivity, uranium atom has finally become a lead atom. This is not possible according to the third postulate of Dalton's atomic theory. But in modern day science, we know that radioactive elements exist, and we make use of them very often. Fourth postulate of Dalton's atomic theory explains that atoms of different elements combine in simple whole number ratios to form compounds. For an example, we have two elements A and B. The atoms of A and the atoms of B will combine in different whole number ratios to form compounds such as AB, where the ratio among A and B is 1 to 1. It could be A to B, in which the ratio of A to B is 2 to 1. And it could be AB2, where the ratio is 1 to 2. It could be A to B3, something like that, where the ratio is 2 to 3, so and so. For real life examples, we can show that the oxides of nitrogen, for example, nitrogen monoxide, which has a ratio of 1 to 1 between nitrogen and oxygen. We have nitrogen dioxide, which in which the ratio among nitrogen and oxygen is 1 to 2, and we have of course NO3, nitrogen trioxide, where the ratio is 1 to 3, and we have N2O4, again the ratio is 1 to 2. We can simplify this 2 to 4 ratio into 1 to 2, and also nitrogen pentoxide, which has a ratio of 2 to 5. Not just the oxides of nitrogen, all other compounds. For an example, sulfuric acid, H2SO4, which has a ratio of 2 to 1 to 4 between hydrogen, sulfur, and oxygen. Another example is methane, CH4, where the ratio is 1 to 4. Benzene, C6H6, where the ratio is 6 to 6, so 1 to 0, or 1 to 1, simplified. Now, like this, Dalton explained that elements combine in simple whole number ratios to form compounds. But again, even this postulate has a problem with it. For an example, if we take a sugar, now the sugars, for an example, table sugar, The chemical formula for table sugar is C12H22O11. Now in this example, you can see that the ratio is 12 to 22 to 11, and also we cannot simplify this into a simple ratio. So there is an issue with this statement of Dalton's atomic theory, because some compounds do not comply with this statement. For an example, table sugar. Another issue with the atomic theory of Dalton is it fails to explain the presence of allotropic forms of matter. Now, allotropic forms are different physical forms of the same element. For an example, if we consider carbon, one of the most extensively studied elements on Earth, one of the most abundant elements on Earth. Now, if we consider carbon, carbon can exist in different forms, such as diamond, such as coal, graphite, and we have carbon nanotubes, and we have fullerenes. You don't have to know about all of these. Now, all of these things are actually pure carbon, but they look so much different. They have very different chemical and physical properties. For an example, diamond is a very hard material, but coal and graphite are not so hard material. And diamond is transparent while coal and graphite are not. Diamond does not conduct electricity while graphite conducts electricity. So the problem with Dalton's atomic theory is that it fails to describe these properties, these allotropic properties of an element. Not only carbon, but sulfur is also showing some allotropic forms, like monoclinic sulfur and rhombic sulfur. Now these are actually different crystal forms. These are also due to different atomic arrangements. Dalton's atomic theory fails to explain these ideas, therefore it is also another issue with Dalton's atomic theory. Now this is all about today's video lecture, and I hope to see you in another video very soon. Please subscribe to the channel, and if you like this video, press the thumbs up and also press the bell icon so that you get notified when I release my next video. So until then, happy learning.